In this video, you will learn more about how spectroscopy measurements in the field are conducted. The team of the University of Munich is loading the measuring gear into the vans, including spectrometers, LAI meters, chlorophyll meters, storage devices for collecting biomass samples, and yes, also simple tools, such as a folding rule. The weather is fine, the sky is free of clouds. This is going to be a good campaigning day. The vans are heading to a test site called Munich North Isar, which is located in an agricultural area north of Munich, where the LMU team conducts experiments on a regular basis and, in particular, collects spectroscopy ground reference measurements during the overflight time of hyperspectral flight campaigns like the Avirus NG campaign 2021. Once they arrive at the test site, the team immediately starts unloading the equipment. Although all the field equipment is packed in robust cases, the instruments need to be handled with great care. The spectroradiometer especially is almost as vulnerable as it is expensive. When taking it out of the box, the operators make sure that no pressure is exerted on the fiber optic cable. Bending or twisting the cable above a certain degree will lead to longitudinal splice of the optical conductors and will irreversibly damage the cable. To avoid excess mechanical stress, it is best if a second person assists with mounting the instrument in the backpack and with installing all the auxiliary gear. The fully mounted field spectroscopy setup consists of the following parts. First, the spectrometer itself, seated safely in the backpack. Second, a reference panel sealed in a dust-free container. Third, the laptop on a tray. The computer is connected to the instrument via wireless connection and is used for controlling the spectrometer. An adjustable rod is used for holding the fiber optic at an adequate distance from the operator to prevent any influence on the target. Please note that the operator should wear dark clothes to avoid spectral contamination of the measurements. Attached to the rod is the fiber optic cable with a 25-degree aperture. The cable is mounted in a pistol-like grip. On the grip, there is a bubble level that helps to maintain a nadir acquisition angle. Finally, there is the power supply, also attached to the backpack. Equipped like this, the operator looks almost like a character from a Ghostbusters movie, don't you think? Now, let's go through a typical measurement procedure. Our expert Toby will introduce every step necessary.
Every spectroradiometric measurement in the field starts with a sequence of very decisive steps. The first step is we have to adjust the integration time of the instrument to the incoming radiation intensity, and we do so by using a reference panel. The first important step here is to make sure that our tripod here is absolutely level, and we do so by using a bubble level control here. I then place the panel on top of the tripod and we're ready to go.
But what exactly is a reference panel? A reference panel is a very special piece of white synthetic material, such as spectralon, that has a very high and stable reflectance throughout the visible to shortwave infrared spectral range. It is a so-called Lambertian surface, meaning that it reflects light into all directions equally. Please note that as we are moving around the panel, the brightness of the white surface remains constant, whereas the brightness of the grass in the background changes depending on the geometry between the sun, the object, and the observer. If the illumination source and the observer are looking in the same direction, primarily the bright parts of a rough surface are perceived. If the observation angle is oriented towards the sun, the shaded parts of the rough surface dominate the view. The intensity of this effect, which we call the bidirectional distribution function, or BRDF, depends on the geometric complexity of the cropped surface. As the sun continuously progresses on its course across the sky during the day, the illumination angle is slightly different for all measurements, even if the measurements are collected in rapid succession. In addition to the exact location of the measurements, the exact time of each measurement should also be noted down in a dedicated field protocol to allow tracing the spectral effects of the illumination geometry during post-processing.
The second step would be measuring the dark current. The dark current means quantifying the thermally induced noise that happens within the detector. The specific instrument that we are using today does this measurement automatically, so we don't have to do it. The third step then would be to do a reference measurement. Doing a reference measurement means we tell the instrument that the currently incoming amount of radiation should be 100% of the reflectance.
Perfect. Now we are done with the white reference measurement. One thing is very important to add here. The noise in the signal highly depends on the temperature of the instrument. The spectrometer is equipped with internal cooling devices to balance the temperature of the detectors. Letting the spectrometer level out its internal temperature for about 30 minutes before starting the measurements is highly recommended. Okay, Toby, what's next?
The final step then would be the actual measurement.
Let's see what that looks like exactly. The operators carefully walk into the field, trying to avoid damaging the crop, and point the spectrometer to the sampling locations which have been predefined via GPS coordinates. One person is responsible for the correct pointing of the fiber optic, while a second person is controlling the instrument and is keeping track of the stored files. The instrument is configured in such a way that it continuously records spectrum after spectrum and averages the readings. By gently moving the fiber optic above the canopy, while at the same time maintaining the nadir orientation of the aperture with the help of the bubble level, the spatial heterogeneities of the target are captured by the repeated measurements. The single readings then can be post-processed to average spectral signatures of the target, in this case the spectrum of a cereal canopy. In some parts of the spectrum, vegetation is very transparent, for example in the near-infrared. When measuring vegetation with the spectrometer, it is very important to also collect a spectrum of the background, which might be shining through. Here, we measure the optical properties of the underlying soil. In this particular Avirus NG campaign in 2021, a 30 by 30 meter section of a winter wheat field is sampled, which represents 1 pixel of the Nmap satellite. The team carefully executes the measurements, following a predefined sampling pattern. This allows quantifying the subscale variability of the canopy. There are already a lot of environmental satellites available, and with new hyperspectral missions such as Nmap, we will even get full spectral coverage from space. Isn't that fantastic? Okay, then let's sum up. Whenever you plan to carry out field-based measurements with a point spectroradiometer, these tips may help you. Measure under stable illumination conditions with regard to cloud cover, solar angle, and atmospheric composition. The sky should be cloudless and clear, and measurements ideally taken 2 hours around solar noon. Make sure the person taking the measurements wears dark clothes and does not cast a shadow on the target. Make sure that there are no bright, colorful, or reflecting surfaces nearby. Regularly check and possibly repeat white reference measurements. This is also a good indication of changing conditions. If major changes occur, repeat optimization. Depending on the instrument you are using, allow some time for warm-up. In the case of the ASD, the detectors heat up at different rates, leading to artifacts in your spectra at insufficient warm-up. And finally, always keep notes, ideally in a standardized field protocol. Otherwise, you'll never recollect what you've been doing.